Technogenesis. Our bridge from the theoretical to the commercially practical.
The idea is that the faculty are players both in the creation and the implementation of technology.
Technogenesis brings a purpose to education and research. While we are motivated to achieve, in general, excellence in education and research, it is excellence for a purpose.
We start from basic principles, optics, geometry, and what we do is we create knowledge.
It's not just the commercialization of technology, but it's the whole spectrum of activities from the very basic science to the technological aspects of innovation and intellectual property, ultimately to commercialization.
It's evident that our research has lots of promising applications. And actually, applications of our research are pretty broad.
To find the applications that are important and then to work on ways to implement them at low costs.
Our faculty and students work collaboratively with industry to apply the latest thinking in technology management to find new business opportunities, to create wealth for themselves and their corporations, and to create prosperity for the communities in which they live.
Students at Stevens are a crucial part of Technogenesis.
You get to go and work. You get to actually do what your major says you're supposed to do.
To go out and perform, to understand their lingo, to understand the terminology.
When you ever see the eyes of a student when the laser didn't work and he got it to work for the first time on his own, it's amazing, and that pays off a lot.
It gives me something to put on not only my resume, but also it helps me develop many other skills that I'm going to need when I graduate.
Other institutions may deal with a segment of the process, maybe a little bit of research, a little bit of mathematics, a little bit of science. But here at Stevens, we let students, faculty, and administration see the complete development cycle. That's very important.
Why is Technogenesis receiving so much attention and energy on campus, around the country, and across the world? In a word, it's because the educational environment brings together so many important elements that people have realized that it can make a difference.
Academic institutions like Stevens are critical to better understanding the innovation process. Industry tends to get enamored by what their own company does, and they really don't have a bigger perspective of what works at many companies. I think you need academics to play the role of understanding what are some of the key characteristics, the theories, the best practices.
A great invention or a great discovery or a great piece of technology by itself is not enough. Technogenesis and true innovation requires the delivery of something new and better. So it's the management aspects of creating value from science and technology that are crucial.
My research interests are in producing a tiny chemical reactor like this big, which I can carry in my pocket, and that chemical reactor will produce a chemical that we like to have. As an example of that is a hydrogen fuel for a portable fuel cell that might replace small batteries in your cell phones or laptops and some of these futuristic device applications.
Another example of a useful microchemical approach to manufacture hazardous chemicals in amounts as small as possible.
So that would eliminate the need, for storage facilities, and of course that enables safe, production of these chemicals.
At Stevens Institute's Computer Vision Laboratory, the research involves some questions that may seem obvious but are not. What is the color of an object we see exactly? Does the color change if the surface of the object is shiny or dull?
So what we did is we put various objects made of different materials, plastic, ceramic, paper, on a special optic table that we have in the lab. Then we used a high research quality analog camera. We mounted in front of the camera a filter wheel with special narrow bandpass filters, and we captured 8 different color signatures. When we are doing this fine color sampling, we can actually see things that we do not see with our eyes. So we can help procedures that need to identify objects.
When the Oklahoma City Federal Building was bombed in 1995, rescue workers had difficulty telling the human bodies from flesh-colored mannequins in the rubble of a clothing store. That problem helped focus Dr. Angelopoulou's research. Techniques developed at the Computer Vision Laboratory may also be used in other fields, including military target recognition and automobile safety.
The microwave detection for biological warfare defense is actually one of the large multi-university projects that is funded by the Department of Defense. So that is actually going on in my own laboratory right now. And other schools are involved with coming up with new sources of radiation, detectors of radiation. But we're actually concerned with how to detect.
And once detected, how to eliminate biological threats.
With optics, we have found a way to create pulses or peaks or excitation which are much shorter. Ultra-short laser pulses, they are the tool which will open us the access to the future of electronics, communication, and everything that we have. It all will depend on how fast you can switch, how fast will be semiconductor in the future.
Nanobiology is the science of life in small form, organic molecules, microbes, single-cell structures, the materials with which they interact, and how the interaction may be put to use.
In particular, I'm talking about drug delivery applications.
Dr. Svetlana Shukashvili's research involves the phased release of drugs in minuscule amounts within the body.
Controllably release this active ingredient at any specific conditions, pH, ionic strength, or electric field required by the particular application.
I'm really taking a twofold approach to studying polymers. On the one hand, I use powerful electron microscopes to study the structure of polymers and polymer-based materials for a variety of different applications. And at the other extreme, I'm using these same electron microscopes as materials processing tools to do electron beam lithography, to pattern surfaces using different types of polymers, especially for biologically relevant applications.
Stochastic optimization. If you know the term, you know that investors use it to manage risk in a seemingly unmanageable world.
Today, investment decisions are very complicated. They involve issues that are of global nature, issues of timing, issues of the uncertainties in business, and all of these introduce complexity in making a decision. It is so complex that the decision-making process needs to be modeled mathematically.
I try to create mathematical models. What is the best decision among all possible decisions which will achieve your goals?
Stochastic optimization is the model-making process. In the Stevens Department of Mathematical Sciences, innovative computational methods are devised, perfected, and tailored to the investment community.
This helps reduce the risk in a major financial investment.
I like to think that the written record is still the most important record that we as a civilization can establish. That may be transcended in the future by things that appear on the computer, but after all, they are written as well. So you have to know how to write. This effectively enables communication. It also enables memory.
At Stevens Institute of Technology, students learn communication in the Department of Humanities and Social Sciences.
We need leaders in the scientific community who can think, who can speak, who can communicate, who know about the history of the species, who know what its mistakes have been, and who might be able rationally to explain policy.
Part of our mission is to see our research find its way into the marketplace and benefit society.
At Stevens, that mission may be seen clearly at 5 research and development centers, each committed to the technogenesis approach.
The Design and Manufacturing Institutes, by doing cutting-edge research and development, prepare students in dealing with real problems in a real settings with technologies that they see in industry when they leave Stevens.
DMI's main focus is on computer software for designing virtual prototypes of products and systems, so that before actual construction, engineers may evaluate the effect of variations in shape and dimensions, materials, and cost, and so assess the product's likely life cycle and profitability.
If you look at our technology to improve manufacturing, reduce the cost while having high-quality products, all of these are having national impact.
This center at Stevens develops technologies for fighting pollution.
One deals with treatment of water contaminated with heavy metals.
Stevens scientists developed an innovative, inexpensive method of removing arsenic from village wells in Bangladesh.
Each family can use a small filter, no electricity, no pumping.
This process has saved thousands of people from poisoning. A second major focus for the Center for Environmental Systems
is a plasma technology that has applications in a wide variety of areas, including air pollution control and microbial control in surfaces and sterilization.
These cold plasma applications may be used, for example, to remove chemical and biological contamination that might result from terrorism.
The restoration of the Everglades is a major challenge, environmental challenge for our nation and for the world actually, because it's a unique ecosystem. We're in contact with the South Florida Water Management District to look at a specific problem that they have, namely the removal of phosphates and phosphorus from the Everglades. We work with NASA as part of NJ-ENSCORT, which is a center for research and training, a center supported by NASA. Our objective in that effort was to develop technology that can be applied in space. Actually, we helped them develop technology that can be applied on a space station or on a spacecraft that's going to Mars.
We'll tell you more about technologies developed at the Center for Environmental Systems in our commercialization section.
WinSec is our wireless network security center, and their focus is on wireless security. They have produced very interesting research which has led to the wireless network radio.
The field is wide open, changing just as quickly as the use of wireless technology is growing.
You're making a call on your cell phone and the call often drops or you have interference. But there are channels that are available that are underutilized. So this radio will find those channels, and that's sort of akin to frequency hopping, but it goes beyond that because it'll take the signal and it will divide it among the available channels. So the concept of this wireless network radio is now the seed behind a new startup company that we have just started, and it's called Attila Technologies.
Stevens is one of the first to have really made a major push in wireless security. By being first, I think Stevens has the opportunity to basically shape where the research is going to go over the next 5 years. So in my mind, 5 years from now, we'll be seeing Stevens as one of the leaders in the country in a very, very important new field for the economy and for the security of the country.
The Center for Maritime Systems will be the most advanced research facility in the world in the area of ocean engineering and marine environmental engineering.
Research on that topic is already underway at the center. Another important focus of the center is terrorism, specifically bombs or other threats which may be carried in any of tens of thousands of ships which enter American ports each year. The center is helping to develop sophisticated detection devices, which conceivably could save millions of lives.
I don't think we can think of very many issues that are more at the forefront of people's minds right now than port security and environmental quality.
What are highly filled materials? They are dense, thick, often weighty substances. Think of moldable plastic, bar soap, chocolate.
These materials need to be processed within a very narrow temperature range. The material has to come to a state where it can flow and be processed. Being able to keep the process under control, designing machinery to keep the cooling rates at the desired ranges, etc., all become challenges.
Dr. Kalyan and his colleagues devise ways to improve the manufacturing and processing of highly filled materials. Other examples include solid rocket fuel, some ceramics, explosives, and epoxy coatings for computer chips. As at all of Stevens development centers, students take part.
To exercise their own brain power in a way so that they could come up with technologies and products which would benefit the society.
Getting technology out quickly in a way that meets the needs of the consumer, whether it be an individual consumer or the corporate business consumer, is constantly a challenge.
Students from a senior design class in biomedical engineering had applied or are applying for a patent, and the patent's actually pending, for a unique application of a stent. And the students were so enthusiastic about their project that they actually returned after they graduated to apply for the patent.
A brainstorm. When you have one at Stevens, there's a structure in place to make it real. But it isn't enough to encourage faculty and students to take their ideas to the marketplace. At Stevens, we help them do it.
The